This is IAQ Radio, Indoor Air Quality Radio, the voice of the indoor air quality industry, with your host, Radio Joe Hughes, and the Z-Man, Cliff Zlotnick. And now, Radio Joe Hughes.
Good day and welcome to IAQ Radio Plus. We've got a great research to practice show for you today. We've got Dr. Rachel Adams on. We're going to talk about moisture measurement and mold. Please check out the Facebook page and our YouTube page. Leave a comment and subscribe on our IAQradio.com homepage. Before we get started, let's thank our platinum sponsor.
IAQ Radio Platinum sponsor is John Don Products, where restoration and abatement contractors shop. Visit them at jondon.com. That's JONDON.com.
I also want to thank our gold sponsors, Particles Plus, Healthy Indoors Magazine, Gray Wolf Sensing Solutions, and AEML Inc. Laboratory. And of course, our association sponsors, the Indoor Air Quality Association and the Restoration Industry Association.
And now you can win a cool prize. It's time for the IAQ Radio Trivia question. Be the first to correctly answer. Simply email your answer to czlotnick@cs.com. Or if listening live, just text your answer from your computer. And now, here's the Z-Man with this week's IAQ Radio Trivia question.
Hello, everyone. I'm sorry to report no one correctly identified the Clean Air Act of 1963 as creating a research and regulatory program in the U.S. Public Health Service. The IQ Radio Trivia question for today, Friday, March 29, 2019, has been sponsored by Ideas, the solution chemistry company, providing unique solutions to odor removal, surface cleaning, and decontamination problems. Here is today's trivia question. Name the scientist who in 1953 established bacterial growth correlated to water activity, not water content. Back to you, Joe.
Quite appropriate for today's show. All right, today's guest is Dr. Rachel Adams. She's a microbiologist with the California Department of Public Health and a project scientist at the University of California, Berkeley, in the Department of Plant and Microbial Biology. Dr. Adams has expertise in using sequence-based technology to study microbial exposures in indoor environments, has developed methods to improve the identification of microbes, and has interest in understanding the consequences of indoor microbial exposure on human health. She's got her BS from Georgetown University, a PhD from Stanford, and she's a member of several of the associations out there, related associations. Hello, Dr. Adams. Do we have you?
Yes, I'm here.
Great to have you. Looking forward to it. It took a little while for us to connect, but we're together now. I was looking a little at your background. You're at UC Berkeley now, so you're in California. You went to school at Stanford, California, Georgetown, which is outside in D.C., and New South Wales. You've been around quite a bit. Can you tell listeners a little bit about your background and how you ended up so interested in microbiology?
Yeah, sure. So I grew up sort of with just a natural interest in nature and biological diversity. And when I went to college, I studied biology as an undergrad research major, and through research got exposed to hidden diversity, so diversity that we can't see with our eyes. So either that's genetic diversity within species, or lots of life that is too small to see. So ever since then, I've been studying sort of this hidden diversity in nature, and trying to understand how that's generated, and then the consequences of that hidden diversity on larger processes that we can see.
You're with two groups there, UC Berkeley and the California Department of Public Health. There's a lot of, departments of public health have to deal a lot with moisture and mold issues. And I kind of wanted to start with how California is handling mold in homes. Can you tell listeners a little bit about how the California public health groups deal with, calls or letters about mold in their home, or maybe they're renting a home, or they're working in a building that has moisture and mold issues?
Yeah, so this is an interesting topic, one I'm getting more and more sort of fascinated with. My background is pure research, but part of our job, part of my job at the working with the state of California is doing sort of public outreach and public education. So while I'm in the indoor air quality group in the environmental health laboratory branch, and so we ourselves do not do inspection or regulation. So we're tasked with doing research related to the causes and ultimately the prevention of pollution in indoor environments. So our mandate is really basic science, basic research, but part of that involves educating the public about some of these issues. So we have statements on relationships between dampness and health, and we have advice documents on mold or moisture in my home. What do I do? But we do get a lot of direct inquiries from renters that have mold in their homes and don't know what to do. So one of the things that we did was we created a database for the entire state. So you could go to the database and enter your city and your county and find out who should be helping you if you have mold in your rental home. And there's a lot of sort of complications in that. So basically, the housing code was amended semi-recently to include mold as a factor that made a building substandard. So dampness has been in there, but semi-recently it added mold. And so the state housing code regulates that local agencies should enforce the housing code, but it doesn't actually specify who or how that's actually executed. So it's left to the county and the city to figure that out. And so everywhere in the state, it's a different agency, or it's a different sort of jurisdiction, whether it's in your city or your county. And then even within that, it might be different departments. So it might be code enforcement or environmental health, or but I guess those are the main ones that we see. So there's a lot of variation in where people go to get help, and it's not very clear. And so one thing that we're trying to do is sort of improve that information and make it easier for people to find out how to get help if they have mold in their rental home.
And you mentioned that, and I'd like to clarify, was it California that added mold, or was it a federal?
No, it was in the California Housing Code. It added mold as one of the factors. There's a list of 15 factors or something that make a unit or make a structure substandard. So there's things like they don't have running water, or things like that. And so dampness in habitable rooms was always on there, but now visible mold was added as a bullet point.
I see. All right, let's talk a little bit more about if a landlord. Let me add, if a landlord doesn't want to obviously spend a bunch of money fixing the mold, is there recourse? Can code enforcement go out and then point to this California code and say, hey, you have to do X, Y, or Z?
Yes. So officially, the local jurisdiction has full authority to cite the landlord, deem that unit uninhabitable, and the landlord has to fix it.
Oh, okay. And
so in theory, this is on the books. I mean, what we find is sort of a lot of variation in how that's actually enforced, whether it's actually enforced, sort of the knowledge and experience of the code enforcers to know to even know that they have the power to do that or the will to do that. So, so officially, yes, someone has the right to tell that landlord they need to fix that.
Do they then reference a particular guidance document that, you know, the landlord has to follow when fixing that? And then is there some way of confirming it's been fixed?
No. So this is all up to that particular code enforcer, whether it was sufficiently addressed.
Interesting. It's tough. That's a tough situation for many states. And I was watching some TV this morning. You're not only a state in California, you're the 5th biggest economy in the world. So
we hear that a lot. Yes.
Yeah, that's amazing. All right, so let's talk a little bit about the ASHRAE journal article that really kind of I've been wanting to get you on for a long time. I know you're well known in the whole research arena when it comes to mold and microbial issues. But then I saw this article on measuring building moisture to thwart mold growth that was in the ASHRAE journal. I can't remember, that was in February. And then I contacted you after that to see if we could talk a little bit about it. I thought it was interesting. The article and your co-author was Mark Mendel. We've had Dr. Mendel on the show. I'm a little disappointed to see it was 2011, so we need to get him back. We were talking about, at that point, a great show, by the way, and we did replay it once, but it was about health effects associated with mold exposure. And he had done a very interesting, I guess, what do you call it when you look at a whole bunch of different papers and then you put like meta-analysis,
right?
Okay, he did a meta-analysis and it was on bronchitis. A lot of it was related to bronchitis and mold health effects. I'm just curious that, since that was 2011, I noticed in the editorial you sent me that they're including development of asthma as a potential health effect associated with mold. Are there other things that have been updated since that 2011 article?
There is. Mark has also done another. Mark and others have also done, I think it's a 2015 study. That's also from a new meta-analysis where they looked at different studies and whether the data showed whether it was sufficient to cause these, or as a cause for some of these other respiratory ailments, or just associated. And so that 2015 study, what showed that it was, I believe this is right, that there was enough evidence to show that it actually exacerbated asthma and associated with new asthma. I would need to look, but
okay.
There is a new paper since the 2011 one.
Okay, we'll definitely get that. I'm going to try hard to get. After reading the editorial you wrote, I'd like to get both of you on. It's fascinating, and it's very related to what we call our research to practice series. We're trying to get practitioners the most current information on, what researchers are finding with respect to these indoor air quality issues. And the one I read in the ASHRAE journal was about measuring building moisture. I noticed in there it said that an estimated 20 to 50% of homes have one or more signs of dampness. And I'm curious where those numbers come from and how they define dampness. Yeah,
so those papers numbers come from a series of studies. So 3 in particular, and these are all sort of a compilation of other studies. So the 3 papers are an Institute of Medicine paper that was looking at indoor air quality. And then there's a WHO report that also was looking at dampness and mold. And then there's a paper in indoor air by Maduri and Fisk. And these papers just looked at the available papers out there and tried to get sort of summary data about that. So the 20% is coming from the WHO and the Institute of Medicine estimate. And then the 50% is coming from the Maduri and Fisk paper. And so we'd have to look in those papers for the individual studies that they were drawing from. But part of the issue is that all of these papers sort of looked for different aspects of indoor dampness and mold, and so it's hard to sort of compare it quantitatively. You kind of just have to look at it qualitatively and see what the similarities and differences are. But most of these studies were based on questionnaires or self-reported questionnaires to homeowners, asking them questions like, how often have you seen mold? Is there visible mold? Is there visible dampness? Is there odor? Do you have condensation on the windows? So these sort of questions, and then it's the sort of survey-based responses.
I know you had a follow-up. I don't know if it was to that or to an earlier question. Please jump in.
Oh, Joe, it was to actually a previous question dealing with occupants who have a mold issue.
Mm-hmm.
And I recently did a mold investigation. It was a Section 8 property. And I went out there, and there was a serious fungal contamination in the apartment. And the tenant had turned in the owner of the property to the health department and so on and so forth. And what I found out when I went out there is I found that the problem was this woman had actually invested in a washer-dryer unit that did both. It washed the clothes, it also dried the clothes, and it was not vented to the outside.
Mm-hmm.
So essentially, she would wash her clothes, put them in the dryer. When she ran the dryer, the whole house filled with moisture.
Mm-hmm.
Green stuff's growing everywhere, and she kind of thought it was the landlord's fault. And I just wonder if you ever run into any situations where it's not the landlord's fault, it's in fact the occupant's fault, and what happens in those situations.
Yeah, so we don't do inspections, so I can tell you what gets reported to us. So all that that would sort of fall to the code enforcer to recognize the ultimate source of the problem and then correct accordingly. So in that case, they would be telling the tenant that they need to vent and not necessarily citing the landlord. But I mean, in my experience, it's more often the other way, where
Understood.
Landlords like to think it's the tenant's problem, that it's their fault, not something structural to the building.
Understood.
All right. Well, let's talk a little bit more about, we're talking about mold and moisture in homes and people's residences. 20 to 50% was the figure in the paper, that an estimated 20 to 50% have one or more signs of dampness. You also got into some pretty significant detail about measuring moisture, and that's what we kind of titled this show today: Research to Practice, Moisture Measurement, and Mold. And John put up a slide here that says microbiologists usually express, and I, of course, covered it up with my other, moisture requirements of a microorganism at a minimum of water activity, a measure of how much free water is in a material. So I'm just curious, within that paper, how many of the different papers or studies you looked at actually used water activity, and when did water activity become the go-to measurement?
Well, I mean, water activity, the importance of water activity really grew out of the food industry movement. This realization that wasn't the water content of the food that was going to determine whether mold could grow. It was how much of that water was actually available to microorganisms to grow. So, for example, something like honey or jam actually is, it seems like it's plenty moist, but the water is chemically bound and therefore not available to the microorganisms, and therefore doesn't go bad very quickly.
Wow, that's a fascinating example. I never thought of it that way. Okay.
So that sort of idea applied to the built environment world is sort of the same idea, that there might be water, a building material might have is going to have a moisture content, but it doesn't mean that all that water is available to microorganisms.
Okay, very interesting. Go ahead.
And so ultimately that's what we want to know is, can microorganisms grow? And so the ideal variable for that is water activity. But what you get into at the practical level is that it's not very easy to get at that. So when it's a food, when it's a small material like a food, they do have these countertop water activity measures where you put your food item in a cup, put it in this small tabletop device, and within seconds it gives you a water activity reading. But obviously you can't do that for your building material.
Mm-hmm.
So that's the disconnect there. And go ahead.
Well, I was just going to ask, the ones for food, you said they pretty quickly. I mean, how quickly can you get that? It seems like the ones I've seen for buildings, it takes forever.
Right. And we can talk about that because that's what we found. I've actually never used it, but my impression is that this thing is within seconds or minutes.
Interesting.
But other people who use it will be able to answer that better.
Let's talk a little bit about moisture meters and how that's different from water activity. I know, John, we put some slides together from the article. I'm not sure what do you got up there?
Joe, while he's doing that, 1953 was when the connection was made. And we're the smartest audience ever, right? These guys get these questions in seconds. And the guy named W.J. Scott established the correlation in 1953. So long time ago.
And his research was based on food.
Yes, he was looking for bacterial growth in food.
All right, well, let's talk a little bit about using moisture meters and what are some of the problems with using a moisture meter for determining whether or not there's enough water activity for mold growth?
Well, I mean, at the basic level, moisture meters are measuring some aspect of moisture content or moisture in the material. They're not necessarily measuring the water that's available for microbial growth at the surface. So those things are going to be related, but not necessarily in a straightforward way. So the reason, we can talk about this, but the issue is that at this point we can only say that any fungal growth in your home is associated with a health risk. So it's not dependent on the particular species or the particular type of fungus. It's just if you can see mold, there's an increased health risk, and we know that the more mold you see, the worse the risk is. But there's no scientific studies that show that certain molds are worse than others. So for example, if you have 2 square foot of a particular species, you can ignore it, but you have 2 square foot of another fungal species, then you need to address it. Like that's not been established. So at this point, the fundamental aspect of a building that we care about is whether you're going to get any fungal growth or any sort of microbial growth. And the one variable that determines that is going to be water activity. So really focusing on how much water in a building that's available for growth is at this point sort of the fundamental question and the fundamental goal of inspecting homes for health.
Joe, I think one point to build on what she said, you can have a building that's very, very dry, but you just happen to have a pinhole leak. And that pinhole leak that's wetting surfaces, you're going to have fungal growth on that wet surface, but you're not necessarily going to have significant fungal amplification anywhere else in the building except where it's wet. And all it takes is a little leak, and you can have problems in a dry building.
Yeah, exactly.
So,
Well, but one of the issues for practitioners is trying to get, the tools that we have. We have moisture meters, we have thermal imaging, we have, basic tools for measuring moisture. How well do they relate to water activity?
Yeah, so that was kind of that was what we were trying to get at in this paper. So we were building on work by a colleague in our group, Janet Mocker, who you guys might know from the Bioaerosols Handbook. So she edited
Yes.
that. So she started this project where looking at a single piece of gypsum board and various indwelling and surface moisture meters, how do those correlate with water activity, and starting to look systematically at this relationship between what your moisture meter is telling you and what that water activity is, and therefore how likely it is for you to get fungal or microbial growth. And so what we were doing is we were expanding on that by using different types of drywall materials. And the goal was never to sort of look at the process of how one would then translate your moisture meter reading to a water activity reading, and is that sort of a practical approach, because it would depend on your meter reading, I mean the actual meter that you're using, the board type that you're measuring it on, and some history about whether it's wetting or drying. And so you can imagine this sort of a table being generated that says, if you're using this moisture meter reading on this type of surface, and your meter reading is telling you 0.2, for example, then that correlates. You could look up into this table and it would tell you that correlates to a water activity of 0.75. I mean, that's an example. That was the sort of the concept that we were trying to get at.
That's what you were hoping for, essentially.
Yeah. I mean, not to actually develop all those tables, but to sort of see the feasibility and the accurate and sort of what that process would be like.
And how did it come out?
Well, it turns out it would be a pretty difficult endeavor, I think. So what you're showing is our data in the context of for given critical values of water activity. So we haven't talked about this, but there's debate about what water activity level should you maximally allow in a home, or what's sort of the threshold at which you can say this is safe, nothing is going to grow. And so people generally use something like between 0.75 and 0.85 as sort of the goal for what you're trying to get below to prevent microbial proliferation. So what this study was, or what this particular graph is showing, is for these critical values of AW, what were the moisture meter readings at these different levels? And we were specifically asking things like, do they sufficiently separate? So for example, could the same moisture meter reading be applied to a water activity of 0.8 and 0.85? That's not discriminating between these two critical values, and therefore it may not be informative in that way. So we were trying to compare sort of the how practical it would be to actually glean AW information from these water activities, from these moisture meter readings for these critical AW values.
So you took the same material. I'm just
four different materials.
Okay, and then you looked at both the water activity as measured by.
So we created the water activity levels.
Okay.
we had a glove box. So the glove box is basically just, you know, a sealed chamber that is creates different conditions than what's outside it, and then there's gloves that go inside the chamber so you can sort of manipulate what's going on inside.
Okay.
So it's like, you know, people worked with Ebola. Imagine that, right? But
We're like asbestos abatement workers. They put their hands in a glove bag.
okay. But in this case, we're not worried about stuff getting out. We're worried about the room RH getting in. So we sort of create this field space, create a particular water activity by changing the relative humidity of this sealed chamber and letting it equilibrate for a week to get to that particular water activity.
Wow. Let the material in the box equilibrate for a week.
Yes.
Okay.
So it's equilibrating for a week at this various ERHs at the various relative humidities, and then we sort of show that after a week it's equilibrated to that, so the material is the same relative humidity as the air. So we know the water activity of these different board types, and then we applied various moisture meters to it and recorded what those readings were. And that's what these data are showing, part of what these data are showing. So for example, the one at the top left, the pin P, so we looked at pin and pinless moisture meter readings. But so for example, this one at the low water activity level of 0.75, for the different board types, we were getting readings between, 14 and 16. And then as you went up to, a moisture water activity level of 18 or 19, we were getting readings of, 18 and above, something like that.
I'm wondering, one of the things you said kind of struck me. So you would set up the relative humidity in the chamber, we'll call it a chamber for lack of a better term here, and then you put the material in there for a week. What was that based on? I mean, is it because there was other research that showed after a week that material would come into equilibrium relative humidity or would be at the water activity of the air?
Yeah, I mean, so that was we don't know of any data that have specifically showed that. We just sort of did a practical consideration of long enough to equilibrate, but we did confirm that after a week, we had some board types that were not being manipulated by us, that were sitting in the corner, and that had permanent sort of indwelling meters. And so we could look at the moisture content and the AW of those meters and sort of confirm that they weren't changing, that they had sort of reached the ambient air relative humidity.
I think that's interesting because, we oftentimes are in the field, we're kind of stuck with, last year, for instance, there was a high relative humidity, at least in my part of the country, for a long period of time. And it's always been something I wonder about, how long does it take before the materials that are exposed to a high relative humidity get into equilibrium with that, or, with that air relative humidity. And it looks like a week from what you've done is at least a good starting point. We could say that if it's been exposed to 80% relative humidity for a week, we can pretty much assume that that material will be at a water activity that would be about, 0.8?
Yeah, I mean, I think it's a good starting point, but we would definitely want to do more experiments if that was the particular question. Just because I think a lot of the times we don't know if the material is lagging or the meter that we're using to measure the water is lagging. So those could both be happening, right? That the actual board is lagging in how much it's equilibrium, but then just how quickly whatever meter we're using to measure it is also lagging. And I mean, we did an experiment with a water activity meter and showed, we should talk about that, showed that there's in this particular case, there's a lag in how quickly the meter can pick up the actual moisture or water activity of the board.
Maybe you could expand on that a little now. I mean, just.
Yeah, so one thing that we did was we had a board that was at 85 water activity, 0.85 water activity. It had, and then it had been sitting there, I think at least a week. And then we applied a water activity meter. So a specific meter that measures the water activity of a surface, that works by creating a sealed headspace above the sensor, and then measures the RH of that air in the headspace above the material. And when we did that, the water activity meter started at a 55 water activity level, and it didn't get up to the board water activity level, which was 0.85, for over a day. So there was a sort of extreme lag in how quickly the air in the headspace actually equilibrated with the board.
It took a day. We had the people on from Decagon years ago, and I think it may be the same meter. And Cliff and I thought it was a fascinating show because it was like, maybe we're getting closer to having something that can show us water activity in a reasonable time frame. And I've done it for 20 minutes and found fairly decent.
Yeah, so you see, it instantly jumps. So you do see it start to rise the second you put it on this high water activity meter, but it doesn't get to the ultimate value that it should be at in our hands for 24 hours or over 24 hours.
Fascinating. Hey, we've got to stop and thank our sponsors. When we come back for the second half, I want to mention hysteresis, I think is the term. Talk a little bit about that, and then go a little more into the practical aspects of what you can recommend for listeners with respect to moisture meters. Is that what we're stuck with for now? And then I'd also like to talk a little bit about your editorial that's coming up in Indoor Air. So we'll be back in 90 seconds with Dr. Rachel Adams.
IAQ Radio Platinum sponsor is John Donne Products, where restoration and abatement contractors shop. Visit them at jondon.com. That's JONDON.com. Gold sponsors are Particles Plus engineers and manufacturers of feature-rich particle counters and air quality monitoring instrumentation. Learn more at particlesplus.com. Count on us. Healthy Indoors Magazine, a free online digital magazine for industry professionals and consumers. Subscriptions available at healthyindoors.com. And AEML Laboratories, free FedEx shipping, great pricing, same-day results, and never a rush fee. Learn more at AEMLinc.com. Gray Wolf Sensing Solutions, who use advanced sensor software technology and embedded computers to provide superior environmental test instrumentation. Visit them at wolfsense.com. Association sponsors are the Indoor Air Quality Association, a multidisciplinary organization dedicated to promoting the exchange of indoor environmental information through education and research. Learn more at IAQA.org. And RIA, the Restoration Industry Association, the granddaddy of the restoration industry. Network with leaders. Learn more at restorationindustry.org.
All right, we're back. Second half of our interview, Dr. Rachel Adams. John and I talked during the break. We're going to quickly put up a couple slides we put together to kind of summarize the article real good and pull it together. And then when we get to that hysteresis part, I want you to chime in on that. Go ahead, John. So the first thing was first of all, water activity usually express moisture requirements of water activity at which could grow. AW is a measure of how much free water. We did that. Go to the next one, John. Now, for example, Wallamia seebii, I hope I got that right, will grow at a relatively dry condition of 0.7, while Stachy will grow at a very wet 0.95, and below 0.65 to 0.70, few fungi can grow at all. I want to stop there, Dr. Adams, for just a moment. So below that 65% relative humidity or equilibrium relative humidity, which is approximately a 0.65 water activity, very few, if any, fungi will grow there. That's your area of expertise.
Sure. I mean, I don't do studies where I'm looking at what's the minimum water activity at which fungi will grow, but the general sort of scientific understanding is that below that water activity level, fungi and microorganisms may persist, so it doesn't necessarily kill them to be in an environment that's below that water activity, but they're not thriving, proliferating, growing. So that's the distinction.
Now, what would the other? I'm just curious. I know I'm throwing this out without any preparation, but at what level would the volatile organic compounds that are the byproduct of that growth? Is there a water activity level they have to be at before they start to produce those?
That's a good question, and that is a project that I am actually working on now. So I have a project with colleagues that's just been funded by the Alfred P. Sloan Foundation in their Chemistry of Indoor Environments program, where we're specifically looking at the microbial volatile organic compounds that in indoor building materials at various moisture content levels. So we should be able to answer that in a couple of years.
Couple years. I'd love to get you back for that, because I think that's an area that we don't look enough at, that the VOCs, they're highly irritating for people. And I just, I think of the old Leonard Skinner song, "Ooh, that smell," it's the smell of death, that those VOCs coming off. I find that in homes that have that odor, people have more health issues. And that's just, obviously there's no science behind that, but it's just my practitioner perspective. Let's go to the next one, John. Okay, one more. So different materials can have very different moisture contents. For example, at a water activity of 0.7, Douglas fir has a moisture content of about 9%, while gypsum board has a moisture content of 1%. The same meter gives different moisture readings depending on whether the material is wetting or drying, sorbing or desorbing. This is a well-known phenomenon referred to as hysteresis. I wonder if you could comment on that for listeners just a little bit more.
Sure. It's just this idea that the materials lag in how quickly they release moisture than the amount that they take it up. So if you put a material into a particular high relative humidity, it's going to take up that moisture at a higher rate than if you then move that material to a drier RH, then it will lose that moisture to the air. And so what that means practically in this context is that for a given AW, we know that the available moisture is the same. You get a different moisture content based on your moisture meter readings, whether it's in the process of absorbing water or desorbing that water.
Yeah, I think that's a good practitioner.
Yeah, it just basically creates noise and sort of a range around your moisture meter reading for a given AW.
Okay. And then you noted that instrument scales are not standardized across meters, so different meter models can give quite different readings. How big of a difference did you find there? Was it pretty significant, or?
Yeah, I mean, so we weren't specifically trying to sort of validate certain meters over others. So we weren't thinking about it that way. But first of all, different meters claim to report different things, moisture content, wood moisture equivalent, or just a completely sort of scale that doesn't mean anything, that you just use relative to that meter in another board type. So so that's what we mean, is that there's these scales, they might all give you some number, for example, 14, but that just means a different thing to a different meter.
And I think that's what's made it hard for EPA or others to establish a scale. And they did it in one document, Cliff, you may remember this, in the Hurricane Sandy fact sheet that was on the foaming. At the end of that fact sheet, they had a scale that said, like below 9% was green, 9 to 15 was yellow, above 15 was red. I suspect it's hard to develop one scale for that for every different type of moisture meter. Would you agree, Dr. Adams?
Right, yes. I mean, totally. So I assume that was a wood moisture equivalent scale. They were that particular.
Yes. So
Okay.
They were looking at, after you take the drywall off and you dry the wood, the Douglas fir typically, what level did it have to be before you could start putting your drywall back up?
Right. And so I think we could get to the point where we could say in absolute terms, these are sort of the ranges you would want to be in. If we had done sort of these tables we were talking about how that material type moisture content translates to water activity levels, but sort of that level of detailed research has not been done to my knowledge.
Are you still thinking of doing that, or is there a proposal to do that?
No, not that I know of. We're not planning on doing it, and I don't know of other people that are.
I just think it's something that would help practitioners if we had more of a standardized way of looking at moisture in, even if it was just in wood, let alone, then we start to talk about the moisture in concrete, the moisture in drywall, the moisture in, any number of other materials. It's really tough for practitioners. But anyway, for these reasons, my last bullet point here, moisture meter readings cannot be related directly to the growth potential for microorganisms. I pulled that out of the article and I wanted you to comment on it.
Yeah, I mean, it's sort of a firm statement saying that that a moisture meter reading is not necessarily going to be able to draw a firm line in the sand about whether that material is going to grow, is capable of growing microorganisms. Mm-hmm. That you need a lot of sort of other information than that pure moisture meter reading to say that.
Fair enough. John, do we have another slide? Okay. You say in the article, we tried to bridge this gap by asking the question, could current tools be applied to estimate the water activity? So that's kind of what we were talking about in the first half of the show. One experiment involved timing the response of a sensor available for research but not widely used that directly estimated the AW. Again, we talked about that. And the second approach involved using different commercially available moisture meters on several configurations of gypsum board panels at different water activity levels. I wonder if you could comment on that last bullet point.
So that's the graph where we sort of showed at different water activity levels, what were the different moisture meter readings? How well did they separate out the different water activity measures? And how did they correlate with water activity level? What was the nature of that relationship? And that's where we saw sort of a nonlinear response, and we saw hysteresis.
Exactly. And I think that hysteresis is important for the listeners out there. Now, John, do we have any more slides from that particular section? Okay, so I'm just rushing a little bit because I know we're running a little low on time, and there were a couple other things I wanted to get to. So What tips can you give practitioners on estimating or measuring water activity in building materials?
Well, yeah, this is a little bit of a tough one. I mean, I can say the obstacles, and I can say that there's a lot of room for innovation in this area to develop a practical way to measure AW. But I would say based on what we have now, that it's not practical to measure AW in the field. And so therefore the next best thing are moisture meters. And therefore just sort of recognizing that this connection between moisture meter readings and AW is not, it's not very straightforward.
And I think that's very important for practitioners. You know, we can't do water activity, at least in a way that is economical and practical for practitioners. But we can use moisture meters, but we need to recognize and probably somehow in our reports note the problems with moisture meter readings and trying to convert those into water activity and the ability for mold to grow. Does that kind of make sense to you?
Yeah.
Okay.
Hey, Joe. Yeah, Joe, if I might, you know, to me, there seems to be a disconnect between using a moisture meter that measures moisture content and then trying to get a reading of what's going on at the surface of the material, because those pins are at different depths in the material and so on and so forth. You know, one thing that I can tell you that practitioners can do, and again, I'm not sure exactly how accurate it is or it isn't, but one thing practitioners can do is use a different type of meter. They can use a digital hygrometer. They can take the meter, they can place on the surface that they want to measure water activity in. They can cover it with plastic. They can put tape on it. And those meters quickly react. It doesn't take them hours to react. They're going to react within seconds, and they're going to give you a reading of what's happening in that micro environment. And what's been done in the industry is to take that reading, that humidity reading, and move 2 decimal places over to the left. So essentially, if you got a reading of 80 and you move the decimal point 2 places over, that gives you a reading of 0.8. And again, I'm not sure where it came from. I can tell you that it's used in the restoration industry. It's been used there for years. It's in some restoration literature. I have not seen it in scientific literature. However, I figure a scientist somewhere figured this out and told us, because I think we weren't aware of water activity before, weren't aware of how to measure it. So I think somewhere it's based on science. And that's the one thing that I might suggest to you in terms of future research, is not use try to get I think there's more of a correlation between relative humidity and measuring what's going on in the air and water activity than there is between the moisture content of the material and water activity.
Okay, so the relationship between how quickly sort of these materials actually respond to the RH in the air, and sort of how that then translates to risk for microbial growth?
I think in terms of risk, but also what's going on or what's not going on. And I think what happens is, are you going up or down? Well, the point is, we can have a dry building, and we can go in the building and use all sorts of moisture meters and not find anything. But if we had an area where there was the slow drip, and you can measure the water activity of just that area, with the meter, and number one, prove that it would be prone to microbial growth, or number two, if you had microbial growth, you can have an answer for why you have it, because the water activity is high
in that particular area. But again, these meters are very, I mean, you can buy them inexpensively for and they probably start at maybe $20 or $30 and, you know, then go up into the thousands, but they're pretty accurate. So
yeah, it's just a temperature relative humidity meter.
Right.
You know, and they're
I mean, it sounds like it's the same concept of what is currently in use. It's just the head space is a lot smaller, so it's going to equilibrate much quicker. I'm
not sure how big would the head space be in the meter that you were using in your studies. I mean, how many cubic feet? Or
oh no, I mean it was. I'm trying to remember. It was something like on the order of 2 to 4 cubic centimeters.
Right. So this is going to be larger than that, but it's going to be relatively small. This is going to be, you know, you go to the area that you want to test, and I suspect it has to be somewhat bigger than the meter, or the meter is going to be hanging out on both edges, and we just cover it with plastic and tape it on. So we create a small enclosed head space or enclosed space, and you know, the meters react very, very quickly, so you can get a good idea. And, you know, typically I know, you know, when I've trained people and shown them this particular technique where we would take out, you know, a piece of drywall, and by the time you passed it around a room, it might take 4 or 5 minutes or something like that before everyone had an opportunity to see it. But the thing will, you know, it'll reach equilibrium, and it's going to give you a meter. It's going to get to where it doesn't change.
Okay. Yeah, I mean, that was what we found is, you know, what the meter we were using, it when you put it on the surface, it instantly jumped. So it instantly, but it didn't get to what it was ultimately going to get to for 24 hours.
Right.
This may be, this looks similar to the meter you were using here?
Yes, that's it.
And it attaches to this decagon, I don't know what they're called nowadays, but, you know,
yeah,
this.
It attaches to a sensor, and then that's how the data is recorded, right?
So this I would put on a surface. We'll use my hand as an example, and it encloses a headspace here.
Yes.
Are you aware of any improvements they're trying to make to this? So that the one I have, in my experience, it takes about 20 minutes before you get something fairly stable. And you said it could be up to a day, right?
Right. Yeah, I don't know of if that group is working on it. I mean, I know some academics have talked about trying to what I'm saying, to sort of reduce that headspace so it would go faster. Just something like, you know, a temperature and RH meter directly taped onto a surface or something, something like that.
We're running low on time. I want to jump to the microbiome for just a moment. We've heard a lot about the microbiome and how complicated it is. I mean, we're measuring, you know, thousands of microorganisms in dust, and you know, it can be difficult to figure out what to do with that data. What is new in this area of study, and what is important for practitioners to understand about the microbiome? And I think you sent us a slide that we want to put up here.
Well, I mean, in general, just the microbiome is just the collection of microorganisms in a given habitat. And I mean, I think what's new, so this graph is a slightly different point, but I mean, I think there's a great promise in being able to identify all the microorganisms in a given space or even in a given sample. And so we as sort of scientists are trying to figure out what is the signal in this broad community of microorganisms. What are the particular organisms we care about, and what are the important players? So we're basically trying to find the signal in the noise at this point. And so right now there's great promise in terms of using microbiome-based assays to diagnose health problems or building conditions, but it's still in development.
And if we can jump to this graphic we have up, I'll leave that up here, John. This kind of compares, I think, different types of measurements or observations, and I think it relates them to health effects, if I'm not, if I understand. Maybe you could tell listeners a little bit about this.
Sure. So this was a graph put together by my colleague Mark Mendel, where he was comparing studies that looked at the health risks, so measured health risk, odd ratio, or risk ratio of certain aspects of dampness and mold across different aspects of how we would measure microbes in buildings. And so the left side are quantified microbiological measurements. So you take a sample and you do some assay in the lab, and it gives you some idea of a specific quantity of particular organisms or types of organisms in that sample, and then looks at the associations between those particularly measured microbiological agents and the health outcome. On the right side, these are non-quantified microbiological measurements. But I mean, so the measured moisture is quantified. It's using the moisture meter readings. And then observed dampness and mold are sort of a building inspection level of categories. So things like how much water damage there was there visible mold, was there mold odor? And looking at those aspects of measuring buildings with health outcomes. And curiously, these sort of non-quantified microbiological measurements are much more strongly associated with the health outcome than anything that we can at this point quantify, measure, and assay.
Very interesting.
Yeah, so it's this idea that, you know, going into a building and doing a really thorough survey is going to be able to more strongly predict a health outcome than any sample you could take in that home.
And whether that's a culture sample, a PCR sample, or next-gen sequencing is the NGS, I believe.
Yeah.
And it goes to show that even though we have issues with using moisture meters, they still do pretty darn good when it comes to this scale, and we need to continue to use them as a part of our observations.
Yes, I think there's support for that.
Okay, very good. And then we had one more topic I wanted to get before we go. I know we're running a little over. Can you stay another minute?
Sure.
All right, so you put together a editorial, I think it is for indoor air that's coming up here. You sent me a preview. You and Mark Mendel put together an editorial called "The Challenge for Microbial Measurements in Buildings." And that's been a topic of great interest here on IAQ Radio. What is the takeaway for practitioners from that article? I think this slide we have coming up helps with that.
Yeah, so the figure that we just talked about, that was in that editorial. And it's sort of highlighting the obstacle that quantified microbiological measurements have, because right now they're lagging behind the building inspection and associations with health.
Okay, and I noticed the spore traps aren't on there. I'm curious if you could comment on that.
Yeah, you know,
or slit impact, or whatever you want to call them.
We should talk about, because there are very few academic studies that have systematically used spore traps to diagnose building as being water damaged. We are having a hard time finding peer-reviewed academic papers using that technique.
Interesting. And before we go, any other comments on that editorial that you put together for indoor air, and when will that be in indoor air?
That's coming out online in June.
Okay, great. Great. All right. Well, I know we're running a little over here, but I wanted to give you the last shot. And Cliff, any final thoughts or comments?
I'm good, Joe. Thank you.
Dr. Adams, before we go, is there any final thoughts that you'd like to tell listeners? Anything we missed or anything you'd like to add?
No, I mean, I can just say that I would like to hone into code enforcers that when they see mold, think moisture, and to fix the underlying moisture problem.
And I want to make sure that we put the offer out now that we get you back, and maybe we could get Mark Mendel and talk a little bit about that upcoming editorial and a little bit more about the comparison between different types of instruments that people are using in the field, more on research to practice. I really enjoy these research to practice shows. So thanks for joining us.
Thanks for having me.
All right, this is Radio Joe Hughes saying thanks to this week's guest, Dr. Rachel Adams, to my co-host, the Z-Man, Cliff Zlotnick. At the controls, John, you got to have faith. Most importantly, our loyal listeners, we'll be back next Friday. We're working on a restoration show. I don't quite have it finalized yet, but we'll be back next Friday noon live with the next episode of IAQ Radio Plus.
For IAQ Radio, I'm Spike Reel saying thanks for listening.